Right now, scattered across the universe, objects are crossing invisible boundaries where the fundamental nature of time transforms in ways that challenge everything our intuition tells us about how reality works. These boundaries, called event horizons, mark the point of no return around black holes where gravitational pull becomes so overwhelming that not even light can escape. What happens to time itself at these cosmic edges reveals physics so strange that a single minute measured by someone falling through would correspond to eternity for someone watching from safety. We thought we understood time as a universal constant ticking forward at the same rate everywhere. We built our physical intuitions around the idea that a minute is a minute, whether measured on Earth, on Mars, or in the depths of space. Every clock synchronized properly should agree on how much time has passed between two events. We were profoundly mistaken. Einstein's general theory of relativity, validated through a century of increasingly precise experiments, demonstrates that time itself is flexible, malleable, and dependent on gravitational fields and relative motion. Near massive objects, time flows more slowly than in regions of weaker gravity. This time dilation effect, barely noticeable near Earth's modest gravitational field, becomes extreme near black holes where gravity reaches intensities that warp space-time into configurations so curved that normal intuitions about cause, effect, and temporal sequence completely break down. At the event horizon specifically, the mathematical descriptions of space-time produce a peculiar result. For an observer falling through the horizon, the crossing takes finite time, measured by a wristwatch or biological processes, perhaps a few minutes for a stellar mass black hole, mere fractions of a second for smaller ones. The infalling observer notices nothing particularly special at the horizon itself, crossing smoothly into the interior without encountering any physical barrier or discontinuity. But for an observer remaining outside at a safe distance, watching through a telescope, something entirely different occurs. As the falling object approaches the event horizon, it appears to slow down dramatically. The gravitational time dilation becomes so severe that each second measured on the falling object's clock corresponds to longer and longer intervals as measured by distant observers. At the horizon itself, this dilation becomes infinite. The falling object appears frozen in time, its watch hands stopped, its motion arrested at the very edge of the black hole. This isn't an optical illusion or a limitation of observation. The mathematics of general relativity shows that in the reference frame of the distant observer, an infinite amount of coordinate time passes as the falling object reaches the horizon. The object appears to take forever to complete the final approach, its image growing progressively redder as photons climbing out of the gravitational well lose energy, eventually fading to invisibility as the redshift approaches infinity. These two perspectives, finite crossing time for the infalling observer, infinite time for the distant observer, aren't contradictory, but rather demonstrate the profound observer dependence of time in general relativity. Time is not absolute. Different observers moving through spacetime's curved geometry measure different elapsed times between the same events, and near black holes these differences become extreme rather than subtle. Dr. Kip Thorne, whose theoretical work on black holes and gravitational waves earned him the 2017 Nobel Prize in Physics, emphasized that understanding event horizons requires abandoning intuitive notions about universal time and embracing the geometric picture where spacetime itself possesses structure that different observers slice differently into space and time. The horizon represents a null surface where the geometry changes character in ways that affect how different observers relate to each other. This exploration will take us from the foundations of special relativity through the complexities of curved spacetime, from thought experiments with falling observers to the mathematical formalism describing black hole geometry. We'll examine what happens to time near event horizons from multiple perspectives, why different observers measure such radically different time intervals, and what this reveals about the nature of time itself. We'll discover how black holes serve as natural laboratories, revealing that time is not the universal backdrop we imagine, but rather a coordinate that curves, stretches, and behaves in ways determined by the gravitational fields threading through spacetime. If you're fascinated by physics that forces us to abandon common sense and embrace mathematical descriptions of reality more strange than fiction, subscribe and give this video a thumbs up. And consider this: if time can slow to a stop at event horizons from one perspective while flowing normally from another, what does that tell us about whether the past and future exist objectively or only relative to observers? Comment your thoughts. I'll pin the most insightful response. For most of human history, time seemed obviously universal and absolute. The sun rose and set with predictable regularity. Pendulum clocks ticked at steady rates. Every measurement suggested that time flowed uniformly throughout the universe, providing a cosmic backdrop against which events occurred in definite sequence. Newton formalized this intuition in his Principia, declaring that absolute, true, and mathematical time of itself and from its own nature flows equably without relation to anything external. This Newtonian picture worked brilliantly for describing terrestrial motion, planetary orbits, and everything accessible to 18th and 19th century physics. The predictions matched observations to available precision. No phenomenon demanded reconsidering time's fundamental nature. The idea that a minute might not equal a minute, that clocks might disagree despite functioning perfectly, seemed absurd. Einstein's special relativity in 1905 first challenged this absolute time by showing that observers in relative motion measure different time intervals between the same events. The effect, called time dilation, follows from the constancy of light speed combined with the relativity principle, stating that physics operates identically in all inertial reference frames. Moving clocks run slow compared to stationary clocks, with the effect becoming substantial at velocities approaching light speed. Special relativity's time dilation seems strange enough, but the theory applied only to observers moving at constant velocity through flat space-time free of gravitational fields. Einstein's general relativity, completed in 1915, extended these ideas to include gravity and acceleration, revealing that gravitational fields themselves cause time dilation. Clocks in stronger gravitational fields run slower than clocks in weaker fields, an effect entirely separate from motion-induced dilation. The gravitational time dilation becomes extreme near black holes, where gravitational fields reach intensities impossible to achieve through any other means. At the event horizon, the gravitational potential becomes so negative that time, as measured by distant observers, appears to stop completely. This infinite time dilation creates the apparent paradox where finite crossing time for infalling observers corresponds to infinite coordinate time for distant observers. Three major insights emerge from understanding this phenomenon. First, time is not absolute but observer-dependent, with different observers measuring genuinely different elapsed times between events depending on their motion and gravitational environment. Second, event horizons represent boundaries where space-time geometry transitions between regions that can communicate with distant observers and regions permanently cut off from external observation. Third, the physics describing what falling observers experience differs fundamentally from the physics describing what distant observers see, yet both descriptions remain valid in their respective reference frames. Now let's begin by establishing the foundations of relativity that make these strange effects not just possible, but mathematically inevitable. Foundations of relativity. Understanding. Why time behaves differently near event horizons requires first grasping the principles of special relativity that revolutionized physics by demonstrating that time is not absolute. Special relativity emerged from attempts to reconcile electromagnetic theory, which predicted that light propagates at a specific speed, with the principle that the laws of physics should appear identical to all observers moving at constant velocity relative to each other. The core postulates of special relativity state that the laws of physics operate identically in all inertial reference frames, and that the speed of light in vacuum equals approximately 219,792 kilometers per second, as measured by any inertial observer, regardless of the motion of the light source or observer. These seemingly innocent principles lead to profound consequences when combined through mathematical reasoning. Consider two observers, Alice at rest and Bob, moving at high constant velocity relative to Alice. Both observers possess identical clocks constructed to the same specifications and functioning perfectly. According to Newtonian physics, if 1 hour passes on Alice's clock, 1 hour should pass on Bob's clock regardless of his motion. Measurements might differ due to Doppler effects changing the apparent frequency of signals, but the underlying true time would remain universal. Special relativity reveals that this intuition fails. If Bob moves at velocity v relative to Alice, Alice observes Bob's clock running slow by a factor of gamma. The Lorentz factor, defined as gamma equals 1 divided by the square root of 1 minus v squared divided by c squared, where c represents light speed. For low velocities much less than light speed, gamma approximately equals 1 and time dilation remains negligible. But as velocity approaches light speed, gamma increases without bound and time dilation becomes dramatic. At 90% of light speed, gamma equals approximately 2.29, meaning Alice observes Bob's clock running at about 44% normal rate. 1 hour on Bob's clock corresponds to approximately 2.229 hours on Alice's clock. At 99% light speed, gamma reaches approximately 7.09, and 1 hour for Bob becomes about 7.09 hours for Alice. At 99.9% light speed, gamma exceeds 22, creating time dilation factors of more than 20. Crucially, this time dilation is reciprocal and symmetric. From Bob's perspective, Alice moves at velocity v in the opposite direction, so Bob observes Alice's clock running slow by the same factor gamma. Each observer measures the other's clock as dilated, creating apparent paradox that resolves only through careful consideration of simultaneity's relativity. Events simultaneous in Alice's frame occur at different times in Bob's frame, and vice versa. The physical reality of time dilation has been confirmed through countless experiments. Muons created in the upper atmosphere by cosmic ray impacts possess half-lives of about 2.2 microseconds in their rest frame. At the velocities they achieve, around 99% light speed or higher, they should decay before reaching Earth's surface if we calculate it using only their rest frame lifetime and the distance they must travel. Instead, many muons reach detectors at ground level because their decay is time dilated in Earth's reference frame, giving them effectively longer lifetimes. Particle accelerators routinely accelerate particles to velocities exceeding 99.9999% of light speed, where gamma factors reach thousands. At such speeds, particles live thousands of times longer than their rest frame half-lives would suggest, precisely matching special relativity's predictions. GPS satellites orbiting Earth experience time dilation from their orbital velocity that must be corrected for accurate positioning. Every prediction has been validated to remarkable precision, yet special relativity applies only to inertial observers moving at constant velocity through flat spacetime. Gravity doesn't appear in the theory. Acceleration receives special treatment requiring careful analysis. Einstein recognized that extending relativity to include gravity and acceleration demanded a deeper framework incorporating space-time curvature itself. The equivalence principle provided the key insight leading to general relativity. Einstein realized that observers in freely falling reference frames experience physics identical to inertial observers in flat spacetime. A person in an elevator falling freely in Earth's gravitational field feels weightless, and can perform experiments showing no evidence of gravitational fields. This local equivalence between gravitational fields and acceleration suggested that gravity itself might be understood as space-time curvature rather than a force. General relativity implements this idea through field equations relating space-time curvature to the distribution of mass and energy. Mass and energy tell space-time how to curve. Curved space-time tells mass and energy how to move. The equations admit solutions describing various space-time geometries, including the Schwarzschild solution for non-rotating spherically symmetric black holes and the Kerr solution for rotating black holes. The Schwarzschild geometry provides the framework for understanding event horizons and gravitational time dilation. This solution describes space-time around a non-rotating spherically symmetric mass, m. The metric, the mathematical object specifying space-time geometry, takes a specific form in Schwarzschild coordinates, showing how spatial and temporal intervals relate to each other as functions of radius from the central mass. The Schwarzschild radius, also called the gravitational radius, equals 2gmc2, where g represents Newton's gravitational constant, m the mass, and c light speed. For the Sun's mass, the Schwarzschild radius reaches about 3 kilometers. For Earth's mass, it measures roughly 9 millimeters. These radii remain much smaller than the actual radii of these objects, about 696,000 kilometers for the Sun and 6,371 kilometers for Earth, so the Schwarzschild geometry applies only outside the stellar surface. For black holes, all mass concentrates at radii below the Schwarzschild radius. The Schwarzschild radius defines the event horizon location. At the horizon, space-time geometry exhibits special properties. The time and radial spatial coordinates exchange character. Time-like directions become space-like and vice versa. This coordinate singularity, distinct from the physical singularity at the center, creates the boundary where escape becomes impossible. Gravitational time dilation follows from comparing proper time intervals measured by observers at different positions in the gravitational field. Proper time represents time measured by an ideal clock following the observer's world line through spacetime. For observers at rest at different radial positions in Schwarzschild geometry, proper time intervals relate to coordinate time intervals through factors depending on radius. Far from the black hole where gravitational fields become negligible, coordinate time approximately equals proper time. Closer to the event horizon, proper time intervals for stationary observers become progressively shorter compared to coordinate time intervals measured by distant observers. At radius r, the relationship involves a factor containing the square root of 1 minus the Schwarzschild radius divided by r. As r approaches the Schwarzschild radius, this factor approaches 0, meaning proper time intervals become infinitesimal compared to coordinate time intervals. Clocks closer to the horizon run progressively slower as measured by distant observers. At the horizon itself, the factor reaches exactly 0, clocks appear, stopped from the distant observer's perspective, while continuing to tick normally in their own reference frames. This gravitational time dilation differs conceptually from special relativity's velocity-based time dilation. Gravitational time dilation arises from position in a curved spacetime geometry rather than relative motion. Observers at rest at different gravitational potentials experience different rates of time passage. The effect manifests as a property of spacetime structure itself rather than relative motion between observers. Both types of time dilation occur together in realistic scenarios. Satellites orbiting Earth experience time dilation from both orbital velocity, which slows their clocks relative to ground observers, and reduced gravitational potential at orbital altitude, which speeds their clocks relative to ground observers. GPS satellites at approximately 20,000 kilometer altitude experience net time dilation, where the gravitational effect dominates, causing satellite clocks to run faster than ground clocks by about 38 microseconds per day. Near black hole event horizons, gravitational time dilation becomes so extreme that it dominates all other effects. The proper time experienced by observers hovering at progressively smaller radii above the horizon diverges from coordinate time measured by distant observers. Maintaining position at small radii requires enormous acceleration, opposing gravitational pull, creating additional time dilation from the acceleration itself. Understanding these foundations establishes the framework for examining what happens specifically at event horizons, where gravitational time dilation becomes infinite, and the nature of time itself transforms in ways that create the apparently paradoxical relationship between finite crossing time for infalling observers and infinite coordinate time for distant observers watching the crossing. The nature of event horizons. Event horizons represent boundaries in space-time beyond which events cannot influence observers outside the boundary. The defining characteristic stems from light's behavior. From inside an event horizon, light itself cannot escape to reach external observers, creating an absolute causal barrier. Understanding event horizons requires examining how space-time geometry creates these boundaries and what properties they possess. The term event horizon emphasizes the horizon's relationship to causality and information. Events occurring inside the horizon remain permanently hidden from external observers, lying beyond their observable domain. This differs from mere distance or darkness. Even from billions of light years away, given sufficient time, we could, in principle, receive light from a distant galaxy. But from inside an event horizon, no amount of waiting allows external observers to receive signals or information about internal events. For Schwarzschild black holes, the event horizon exists as a sphere at radius equal to the Schwarzschild radius, 2gmc2. This radius scales linearly with mass. A black hole with twice the mass possesses twice the Schwarzschild radius. A stellar mass black hole of 10 solar masses has a Schwarzschild radius of approximately 30 kilometers. A supermassive black hole like that at our galaxy's center, with mass around 4 million solar masses, possesses a Schwarzschild radius approaching 12 million kilometers, roughly 17 times the Sun's radius. The event horizon is not a physical surface or membrane. No material structure exists at the horizon location. An observer falling through encounters no barrier, feels no transition, experiences no discontinuity. The horizon represents a geometric property of space-time itself rather than a physical object. It marks the location where space-time curvature creates the causal boundary, preventing outward light propagation. Light cones, geometric constructs showing which space-time events a given event can causally influence or be influenced by, illustrate how horizons work. At any space-time event, future and past light cones show the regions accessible through future-directed and past-directed light rays. For observers far from black holes in weakly curved space-time, light cones orient such that future light cones extend upward in time diagrams and outward in space. Approaching a black hole, gravitational effects tilt light cones progressively inward. Future light cones that pointed partially outward far from the hole tip increasingly toward the black hole center as radius decreases. At the event horizon, future light cones tip exactly parallel to the horizon surface. Outward directed light rays travel along the horizon itself rather than escaping to larger radii. Inside the horizon, future light cones tip entirely inward. All future-directed paths, whether followed by light or slower objects, lead toward smaller radii. The singularity at the center lies in every observer's future once they cross the horizon. Escape becomes impossible not because of insufficient velocity, but because outward directions become past-directed in the tilted light cone structure. Moving outward would require traveling into the past, forbidden by causality. This light cone tilting creates the event horizon's defining property without invoking mysterious forces or barriers. The geometry itself determines that nothing crossing the horizon can return to larger radii. The horizon represents the boundary where this geometric prohibition takes effect, separating regions that can communicate with infinity from regions that cannot. The surface area of a Schwarzschild black hole's event horizon equals 4p times the Schwarzschild radius squared, giving area 16pg2m2c4. This area grows quadratically with mass rather than cubically as volume would, reflecting the horizon's nature as a surface in three-dimensional space. The area plays crucial roles in black hole thermodynamics, entropy calculations, and the information paradox. Rotating black holes described by the Kerr solution possess more complex horizon structures. The outer event horizon, analogous to the Schwarzschild horizon, exists at a radius depending on both mass and angular momentum. Inside the outer horizon, an inner horizon called the Cauchy horizon appears in the mathematical solution, though its physical reality remains questionable due to instabilities. The ergosphere, a region outside the Kerr black hole's event horizon where dragging forces all objects to rotate in the same direction as the black hole, creates possibilities for energy extraction through the Penrose process. Objects entering the ergosphere can split into parts where one falls into the horizon while the other escapes with more energy than the original object possessed, extracting rotational energy from the black hole. Charged black holes described by the Reisner-Nordström solution possess inner and outer horizons separated by regions where the geometry becomes highly unusual. Extreme cases where charge equals mass in appropriate units produce horizons that coincide, creating extremal black holes with special properties. These mathematical solutions may not represent realistic astrophysical objects since charge likely gets neutralized in realistic conditions. The no-hair theorem states that stationary black holes in general relativity are characterized completely by three parameters: mass, angular momentum, and electric charge. All other information about the matter that formed the black hole disappears behind the event horizon, becoming inaccessible to external observers. The horizon, in this sense, erases detailed information about what fell in, preserving only these three numbers. Horizon dynamics describe how event horizons evolve when matter falls in or when black holes merge. Adding mass increases the horizon area. The area increase theorem, proven by Stephen Hawking, states that classical processes cannot decrease black hole horizon area, analogous to entropy's increase in thermodynamics. This analogy becomes exact in black hole thermodynamics, where horizon area relates directly to entropy. Hawking radiation, a quantum mechanical effect, predicts that black holes emit thermal radiation with temperature inversely proportional to mass. For stellar mass black holes, Hawking temperatures reach only nanokelvin levels, are below cosmic microwave background temperature. But Hawking radiation carries energy away from black holes, causing them to lose mass and eventually evaporate completely over timescales vastly exceeding the current age of the universe for stellar and larger masses. The information paradox arises from combining Hawking radiation's thermal nature with quantum mechanics' requirement that information be preserved. If thermal radiation carries no information about what fell into a black hole, and if black holes eventually evaporate completely, where does the information about infalling matter go? This paradox remains unresolved despite decades of research, potentially pointing toward new physics beyond general relativity and quantum field theory. Event horizon detection relies on indirect evidence since the horizon itself emits nothing. Astronomers identify black holes through their gravitational effects on nearby matter, through accretion disk emission from materials spiraling inward, and through gravitational waves from merging black holes. The Event Horizon Telescope collaboration imaged the shadow of the supermassive black hole in galaxy M87, showing the dark region created by the event horizon silhouetted against glowing accretion disk material. Apparent horizons, Surfaces where outward-directed light rays remain at constant radius rather than escaping provide alternative definitions useful in dynamical situations where spacetime geometry evolves. For stationary black holes, event and apparent horizons coincide. During black hole formation or merger, they differ temporarily as the spacetime settles into equilibrium. The distinction between coordinate and physical properties becomes crucial when discussing horizons. Coordinate singularities, where coordinate systems become ill-behaved but physics remains smooth, occur at Schwarzschild horizons in Schwarzschild coordinates. Switching to alternative coordinates like Kruskal-Shekera's coordinates removes this coordinate singularity, showing clearly that infalling observers cross smoothly without encountering physical infinities. Physical singularities like those at black hole centers represent genuine infinities in space-time curvature, where general relativity breaks down and quantum gravity becomes necessary. The horizon protects external observers from seeing these singularities directly. The cosmic censorship conjecture proposes that singularities remain hidden behind horizons in physically realistic situations, though rigorous proofs remain elusive. Understanding event horizons as geometric boundaries in curved spacetime rather than physical surfaces provides the foundation for examining why time behaves so strangely near these boundaries and how the different perspectives of infalling and distant observers relate to each other while measuring vastly different time intervals for the same events. Gravitational time dilation. Gravitational time dilation describes how time passes at different rates depending on position in a gravitational field, with clocks in stronger gravitational potentials running slower than clocks in weaker potentials. This effect follows directly from general relativity's geometric interpretation of gravity, where massive objects curve spacetime and proper time intervals depend on the specific path followed through curved spacetime geometry. The mathematical expression for gravitational time dilation in Schwarzschild geometry relates proper time t measured by a stationary observer at radius r to coordinate time t measured by distant observers through the relationship dt Geschwindigkeit 1 2gm rc2 dt. The square root factor, often written as 1 rsr, where rs represents the Schwarzschild radius, quantifies how much slower proper time passes compared to coordinate time. Far from the black hole, where r greatly exceeds rs, the factor approaches unity and proper time nearly equals coordinate time. At radius equal to 10 Schwarzschild radii, the factor equals approximately 0.95, meaning clocks run about 5% slower than distant clocks. At 3 Schwarzschild radii, the factor drops to 0.82, creating 18% time dilation. At 2 Schwarzschild radii, it reaches 0.71, corresponding to 29% dilation. Approaching the Schwarzschild radius, the factor decreases rapidly. At radius 1.1 rs, it equals approximately 0.45. Clocks run less than half the rate of distant clocks. At 1.1 res, the factor drops to 0.14, representing 86% time dilation. At the horizon, where r equals rs exactly, the factor reaches 0, indicating infinite time dilation where proper time intervals become infinitesimal compared to coordinate time intervals. This infinite time dilation at the horizon creates the appearance that objects freeze as they approach. Photons emitted by infalling objects at progressively smaller radii reach distant observers at progressively longer intervals. A photon emitted at radius 2 rs reaches the distant observer relatively quickly. A photon emitted at 1.1 rs takes longer. Photons emitted ever closer to rs take exponentially longer to escape, approaching infinite time for photons emitted at the horizon itself. The practical consequence is that distant observers see infalling objects slow down dramatically as they approach the horizon. An object falling from rest at large radius appears to take infinite coordinate time to reach the horizon. The object's image grows progressively dimmer and redder as the gravitational redshift increases without bound. eventually fading to invisibility as photons stretch to infinite wavelengths. Yet for the infalling object, the experience differs completely. Measuring time with a wristwatch or biological processes, the fall from any finite starting radius to the horizon takes finite proper time. For a stellar mass black hole of 10 solar masses, an object falling from rest at the photon sphere radius, 1.5 Schwarzschild radii, crosses the horizon in approximately 30 microseconds of proper time. The object notices nothing special at the horizon crossing itself. This stark difference between perspectives arises because different observers slice space-time differently into space and time. The distant observer's notion of simultaneity, which events occur at the same time, differs from the infalling observer's simultaneity. Events simultaneous for the infalling observer at horizon crossing lie in the infinite future, according to the distant observer's simultaneity definition. The notion of coordinate time itself becomes problematic near horizons. Schwarzschild coordinates, natural for distant observers, become singular at the horizon, where the time coordinate becomes space-like and the radial coordinate becomes time-like. This coordinate singularity doesn't reflect physical infinity, but rather represents a limitation of the chosen coordinate system. Alternative coordinate systems remove this singularity. Eddington-Finkelstein coordinates extend smoothly through the horizon by combining time and radial coordinates in ways that remain well-behaved at RS. Kruskal-Shekera's coordinates provide the maximally extended Schwarzschild solution, revealing the complete spacetime geometry, including regions inaccessible to any single observer. In Kruskal-Shekera's coordinates, infalling world lines cross the horizon smoothly at 45-degree angles on spacetime diagrams. The horizon appears as a null surface, a light-like boundary that light itself follows. Outgoing light rays at the horizon remain at constant radius. Inside the horizon, all time-like and null world lines lead toward decreasing radius. The singularity at RM0 lies in every observer's future. The gravitational redshift, closely related to time dilation, describes how photon energies and wavelengths change as light climbs out of gravitational wells. A photon emitted at radius r with frequency n, as measured by a local observer, reaches infinity with frequency reduced by the factor 1 RSR. The energy loss compensates for work done against gravity as the photon escapes. For photons emitted near the horizon, the redshift becomes extreme. Light emitted at 1.01 RS arrives at distant observers with wavelength increased by factor approximately 7. Visible red light becomes infrared. Light from 1.01 Ys experiences redshift factor exceeding 22. Light from ever closer to the horizon redshifts without bound, becoming undetectable as wavelength approaches infinity. This infinite redshift combines with infinite time dilation to make the horizon crossing forever invisible to distant observers. Photons emitted at the crossing would require infinite coordinate time to reach distant observers and would arrive with zero energy. The horizon crossing event lies on the boundary of the distant observer's future light cone, an asymptotic limit approached but never actually observed. The physical mechanism behind gravitational time dilation involves the relationship between energy and frequency through quantum mechanics and the equivalence of mass and energy through special relativity. Photons climbing out of gravitational wells lose energy, manifesting as reduced frequency and increased wavelength. Periodic processes using photon frequencies as clocks therefore tick more slowly in stronger gravitational fields as measured by distant observers. This connects to gravitational potential differences. The time dilation factor equals approximately 1 plus Fc2 for weak fields, where F represents the Newtonian gravitational potential. For Earth's surface relative to infinity, the potential difference reaches about 63 million joules per kilogram, creating time dilation factor approximately 0.9 clocks at Earth's surface run slow by roughly 0.7 parts per billion compared to clocks at infinity. For GPS satellites orbiting at approximately 20,000 kilometers altitude, the gravitational potential is less negative than at Earth's surface, causing orbital clocks to run faster than ground clocks by about 45 microseconds per day from gravitational effects alone. Velocity-based time dilation from orbital motion causes the clocks to run slower by about 7 microseconds per day. The net effect, dominated by gravitational time dilation, speeds satellite clocks by approximately 38 microseconds daily. These microsecond-level effects require correction for GPS accuracy. Without accounting for both gravitational and velocity-based time dilation, position errors would accumulate at roughly 10 kilometers per day, rendering the system useless. The necessity of these corrections provides everyday validation of relativity's predictions. Gravitational time dilation has been measured directly through numerous experiments. The Pound-Rebka experiment in 1959 used the Mössbauer effect to measure gravitational redshift over a 22.5-meter vertical distance at Harvard University, confirming predictions to 10% accuracy. Subsequent experiments achieved better precision, validating general relativity's predictions to parts per million. Atomic clocks aboard aircraft and satellites provide increasingly precise tests. Experiments comparing clocks at different altitudes confirm gravitational time dilation predictions to parts in 1016, among the most precise tests of general relativity ever performed. Every measurement confirms that clocks in weaker gravitational fields run faster than clocks in stronger fields by amounts matching theoretical predictions. The implications extend beyond mere clock rates to the fundamental nature of time itself. Time is not an absolute external parameter, but rather a coordinate whose rate of passage depends on space-time geometry. Different observers in different gravitational environments experience genuinely different amounts of proper time between events. There exists no universal, true time against which all clocks should be measured. Near black hole event horizons, these effects reach extremes impossible to achieve through any other means. The infinite gravitational time dilation at the horizon represents the limiting case where proper time at a fixed position becomes arbitrarily small compared to coordinate time measured from infinity. Understanding this extreme dilation provides the key to resolving the apparent paradox of finite crossing time versus infinite coordinate time. The infalling observer. An observer falling toward a black hole. Event horizon experiences the journey as finite in duration and unremarkable in character until tidal forces become significant. Understanding this perspective requires analyzing the infalling world line through curved space-time and recognizing that locally, physics appears identical to flat space-time special relativity. The infalling observer's experience contrasts sharply with what distant observers see, yet both perspectives remain valid descriptions of the same physical events. Consider an astronaut beginning at rest at some large radius from a Schwarzschild black hole and releasing to fall freely toward the center. The astronaut's world line follows a geodesic, the curved space-time analog of a straight line, determined by the space-time geometry. Solving the geodesic equations provides the trajectory through space-time, specifying how radius and time coordinates evolve along the path. For a 10 solar mass black hole with Schwarzschild radius approximately 30 kilometers, an astronaut starting from rest at radius 300 kilometers, 10 Schwarzschild radii, reaches the horizon in proper time approximately 0.15 milliseconds. Starting from 3,000 kilometers takes about 15 milliseconds. Starting from rest at infinite distance and falling all the way to the horizon requires infinite proper time, but starting from any finite radius yields finite crossing time. During the fall, the astronaut's wristwatch ticks normally, measuring proper time along the world line. Each second passes identically to seconds measured during any other uniform motion. Biological processes proceed at their usual rates. The astronaut ages normally according to their own time. Nothing about the passage of proper time suggests anything unusual until tidal effects become significant. The equivalence principle guarantees that locally, in a freely falling reference frame, physics appears identical to special relativity in flat spacetime. The astronaut cannot distinguish their falling reference frame from an inertial frame far from gravitational sources through local experiments. This remains true even at the event horizon. The horizon crossing involves no local physical discontinuity, no barrier encountered, no sign that anything special has occurred. Tidal forces, differences in gravitational acceleration across extended objects, eventually become important as the astronaut falls deeper. These forces arise because different parts of the astronaut's body lie at different radii and experience different gravitational accelerations. The feet, closer to the black hole, accelerate more strongly than the head, creating stretching along the radial direction. Simultaneously, gravitational field lines converge, creating compression in transverse directions. The tidal acceleration difference between head and feet separated by height, h, equals approximately 2g mhr3. At large radii, this remains negligible. At smaller radii, it increases rapidly. For a 10 solar mass black hole at the horizon radius of 30 kilometers, the tidal acceleration across a 2-meter tall astronaut reaches about 106 meters per second squared, roughly 100,000 times Earth's surface gravity. Such extreme tidal forces would certainly prove fatal. Supermassive black holes present different tidal environments. For a billion solar mass black hole like some found at galactic centers, the Schwarzschild radius reaches approximately 3 billion kilometers, roughly 20 astronomical units. At this vastly larger horizon radius, tidal forces at the horizon drop to levels a human could survive. An astronaut could cross such a horizon alive, experiencing nothing particularly dramatic at the crossing moment itself. The astronaut continues falling after crossing the horizon. Inside, all radial directions become time-like, and decreasing radius lies in every future direction. The singularity at RT0 becomes inevitable, lying in the astronaut's future just as tomorrow lies in everyone's future. Attempting to avoid reaching RPB0 makes as much sense as attempting to avoid experiencing tomorrow. Both represent future, time-like directions. The proper time from horizon crossing to reaching the singularity at RWAD0 can be calculated from the metric. For radial infall starting from rest at the horizon, the time equals PRS2c, where RS represents the Schwarzschild radius. For a 10 solar mass black hole, this equals approximately 0.16 milliseconds. The astronaut survives less than 1 millisecond inside the horizon before tidal forces and space-time curvature become infinite at the singularity. What does the astronaut see during the fall? Looking outward toward the stars left behind, light from the external universe continues reaching the infalling observer. Due to the extreme space-time curvature, light paths bend dramatically. The astronaut sees the external universe compressed into a bright ring that shrinks and shifts to higher energies as the fall continues. Blue shift, the opposite of gravitational redshift, increases photon energies from infalling perspective. At the horizon crossing, light from the external universe appears blue-shifted by arbitrarily large factors depending on emission radius and trajectory. In principle, the astronaut could observe the entire future history of the external universe, compressed into the final moments before reaching the singularity. However, the finite light-crossing time for signals to reach the infalling observer and the brief time available between horizon crossing and singularity limit how much future history becomes visible. Looking inward toward the black hole center, the astronaut sees photons that have been falling for various durations. Inside the horizon, no static observers exist. All observers fall inward. The concept of looking inward must account for the fact that inward directions become time-like. What appears inward might actually represent looking at regions already in the past light cone rather than a different spatial location. The astronaut cannot send signals to distant observers after crossing the horizon. Any photons emitted outward simply follow their own inward-pointing future light cones, falling toward smaller radii along with the astronaut. The horizon creates an absolute causal barrier preventing information from inside reaching outside, completing the definition of the event horizon. Communication between infalling observers remains possible briefly inside the horizon. If two astronauts fall along similar trajectories, they can exchange signals until tidal forces or the approach to the singularity makes communication impossible. Light signals sent from the trailing astronaut toward the leading astronaut can catch up and be received. Those signals sent from the leading astronaut cannot propagate backward against the flow toward the singularity. The subjective experience would transition from the normal sensation of free fall, similar to orbiting astronauts in the International Space Station, to increasing tidal stress as R decreases. For small black holes, this transition occurs rapidly. Comfort turns to stress, turns to death within milliseconds. For supermassive holes, the transition might take minutes to hours, allowing extended periods of consciousness inside the horizon before tidal forces become fatal. Does the astronaut notice anything special at the exact moment of crossing the horizon? The answer depends on whether notice refers to local measurements or to larger scale observations. Locally, the equivalence principle guarantees smooth crossing with no physical discontinuity. But the global structure of space-time changes character. The astronaut has entered a region where return becomes impossible and where the singularity lies inevitably in the future. Hypothetically, equipping the astronaut with instruments capable of measuring space-time curvature components might reveal that certain combinations become large near the horizon. But for large black holes, even these curvature components remain modest at the horizon itself, becoming extreme only much closer to the singularity. The horizon represents a coordinate feature rather than a location of maximum curvature. The proper distance from horizon to singularity, measured along a radial path at fixed time, depends on coordinate choice. In Schwarzschild coordinates, this distance formally diverges due to coordinate singularities. In more appropriate coordinates extending through the horizon, the proper distance remains finite. The time available between crossing and reaching the singularity definitively remains finite, measured in microseconds to hours, depending on black hole mass. Recording observations for later transmission fails because no later exists that includes being outside the horizon. Any recordings made inside cannot be recovered by external observers. The information falls to the singularity along with the astronaut. This information sequestration contributes to the black hole information paradox, where information apparently disappears from the universe. Understanding the infalling perspective reveals that horizon crossing involves finite proper time and local physics that remain normal according to the equivalence principle. The dramatic effects occur not for the infalling observer but rather for distant observers watching the approach, as we examine next. The distant observers watching objects fall toward black hole event horizons witness dramatically different phenomena than infalling observers experience. From the safe vantage point far from the black hole, where gravitational effects remain negligible, the falling object appears to slow asymptotically as it approaches the horizon, never quite reaching it in finite coordinate time. Understanding this perspective requires analyzing light propagation from near the horizon and recognizing how extreme time dilation affects observations. Consider a distant observer using a powerful telescope to watch an astronaut falling toward a stellar mass black hole. The observer sees the astronaut by detecting photons emitted from the astronaut's spacecraft or reflected from the astronaut's suit. These photons must propagate from the emission radius through curved spacetime to reach the distant observer's telescope. As the astronaut falls to progressively smaller radii, emitted photons face increasingly extreme gravitational redshift and time dilation. A photon emitted when the astronaut reaches radius 2 Ers and aimed radially outward climbs out of the gravitational well, losing energy and shifting to longer wavelengths. The photon that was visible, light at emission, might become infrared by the time it reaches the distant observer. The gravitational redshift factor equals 1 RS-R for photons emitted radially outward from radius r. At 2 Ers, this equals approximately 1.41. Visible red light at 650 nanometers becomes near infrared at 920 nanometers. At 1.1 Ers, the factor reaches approximately 3.16. Visible light shifts to mid-infrared wavelengths around 2000 nanometers. At 1.0 Ers, the factor exceeds 10, shifting visible light to wavelengths beyond 6000 nanometers in the far infrared. Approaching the horizon, the redshift factor diverges. Photons emitted at radii arbitrarily close to Rs arrive at the distant observer with arbitrarily long wavelengths. The astronaut's image fades from view not because of distance, but because photons redshift beyond detection capabilities. Eventually, the wavelength exceeds meters, kilometers, or astronomical units, making detection impossible. Simultaneously, the rate at which photons arrive at the distant observer decreases. Photons emitted at regular intervals by the astronaut's clock reach the distant observer at progressively longer intervals due to gravitational time dilation. If the astronaut's clock emits 1 photon per second of proper time, the distant observer might receive these photons at intervals of 2 seconds when the astronaut reaches radius 2 Ers, 10 seconds at 1.1 Ers, 100 seconds at 1.0 Ers, and so forth. This reception interval stretches without bound as the horizon approaches. Photons emitted at increasingly closer intervals near the horizon arrive, spaced by increasingly large intervals at the distant observer. The photon emitted at the horizon crossing event would require infinite coordinate time to reach the observer, effectively never arriving. The combined effects of redshift and time dilation create the appearance that the astronaut slows down and freezes at the horizon. The astronaut's image dims, reddens, and appears to halt at the Schwarzschild radius. The distant observer never sees the astronaut cross the horizon in finite observation time. The horizon crossing lies on the boundary of the distant observer's observable universe, an event that occurs but remains forever unobservable. Quantitatively, the coordinate time required for an object starting from rest at radius r0 to fall to radius r approaches infinity as r approaches rs. The falling object's trajectory in Schwarzschild coordinates shows that it takes infinite coordinate time to reach rs even though proper time along the trajectory remains finite. This mathematical fact underlies the distant observer's perspective. Does the object actually reach the horizon, or does it hover eternally just outside? This question contains a subtle confusion about simultaneity. The coordinate time in Schwarzschild coordinates represents simultaneity according to distant observers at rest relative to the black hole. In this simultaneity, the horizon crossing event lies at infinite future time. But simultaneity is observer-dependent, not absolute. From the infalling astronaut's perspective, using proper time along the world line, the crossing occurs at finite time. Different simultaneity definitions give different answers to when the crossing occurs. Neither answer is absolutely correct. Both are valid in their respective reference frames. The physics agrees that crossing takes finite proper time along infalling world lines and infinite coordinate time in Schwarzschild coordinates. The frozen appearance creates the nickname frozen star for black holes in early theoretical discussions. Before the term black hole became standard, researchers debated whether complete collapse to a horizon could occur or whether matter would pile up eternally at the Schwarzschild radius. General relativity unambiguously predicts that complete collapse occurs from the infalling matter's perspective, even though it appears frozen from distant perspectives. What happens if the distant observer waits arbitrarily long, watching the falling astronaut for millions or billions of years? The astronaut's image continues fading and reddening, approaching but never reaching the horizon. Each photon arriving provides information about the astronaut at progressively smaller radii, but never exactly at RS. The infinite sequence of photons approaching the horizon asymptotically provides infinite information in principle, though practical detection limits make observations impossible long before the horizon. Adding Hawking radiation complicates the picture. Black holes emit thermal radiation with temperature inversely proportional to mass. For stellar mass black holes, Hawking temperature reaches only nanokelvins, vastly colder than the cosmic microwave background. But given infinite time, Hawking radiation eventually causes the black hole to evaporate completely. For a 10 solar mass black hole, the evaporation timescale exceeds 1067 years, vastly longer than the current universe age of 1010 years. But if the distant observer literally waits infinite time, the black hole evaporates. What then happens to the frozen astronaut apparently hovering at the disappearing horizon? This question relates to the information paradox, whether information about what fell in gets preserved or destroyed. The distant observer could attempt sending signals to the falling astronaut to communicate or verify observations. Light signals sent toward the astronaut can catch up if sent early enough, but any signal arrives at the astronaut in finite, proper time along the astronaut's world line. The signals don't prevent the astronaut from crossing the horizon or allow communication after crossing. If the distant observer fell into the black hole after the astronaut, following a similar trajectory but delayed, the observer could catch up and meet the astronaut inside the horizon. From this perspective, both observers experience finite proper time falls and can reunite inside. The apparent freezing affects only observers remaining outside at large radii, not observers following infalling trajectories. The coordinate singularity at the horizon in Schwarzschild coordinates creates mathematical infinities that don't represent physical problems. Switching to coordinates that remain well-behaved at the horizon, such as Eddington-Finkelstein or Kruskal-Szekeres coordinates, eliminates these infinities and shows clearly that the horizon represents a smooth, null surface that infalling observers cross without incident. The distant observer's perspective, while mathematically valid, represents a limited view of space-time. The observer's past light cone, the region from which light signals can reach the observer, never includes the interior of the event horizon. Events inside lie outside the observer's causal past. They cannot influence or be observed by the distant observer. This causal structure explains why crossing appears to take infinite time. Comparing distant and infalling perspectives reveals the observer dependence of time in general relativity. The proper time measured along different world lines between the same space-time events can differ dramatically. For the infalling and distant observers, the events of starting the fall and crossing the horizon are separated by microseconds of proper time along the infalling world line, but by infinite coordinate time as defined by distant observers. This doesn't mean time itself becomes infinite. Coordinate time is a coordinate choice, not an observable quantity. Observable quantities include proper times along specific world lines and causal relationships between events. Different coordinate systems describe the same physical geometry using different mathematical representations. Schwarzschild coordinates become singular at the horizon because they're poorly adapted to describing horizon crossings, not because physics becomes singular there. Understanding both perspectives and how they relate provides complete description of black hole horizon physics. The infalling observer's finite proper time crossing and the distant observer's infinite coordinate time observation both represent valid descriptions. The apparent contradiction resolves through recognizing that different observers slice space-time differently and measure different elapsed times between events separated in curved space-time. Inside the horizon, crossing the event horizon transports observers into a region of space-time with radically different causal structure than the external universe. Inside the horizon, all future directions point toward decreasing radius, making arrival at the central singularity inevitable regardless of any actions the observer takes. Understanding the interior requires examining how space-time geometry changes character across the horizon and what this means for physics and causality. The most profound change inside the horizon involves the reversal of time-like and space-like directions. Outside, the radial coordinate r represents space. Observers can choose to move toward larger or smaller radii. The time coordinate t represents time. Observers necessarily move forward in t. At the horizon, these coordinates exchange character. Inside, r becomes time-like and t becomes space-like. This exchange means that decreasing r becomes inevitable just as increasing time is inevitable outside. No more can an observer inside the horizon avoid moving toward smaller r than an observer outside can avoid moving toward future t. The singularity at r-centered 0 lies in every inside observer's future, approached inevitably as proper time advances. Avoiding the singularity would require time travel to the past. The proper time from horizon to singularity equals prs 2c for observers falling radially from rest at the horizon. For a 10 solar mass black hole with rs gestalt 30 kilometers, this equals approximately 0.16 milliseconds. Observers falling from larger radii reach the singularity even faster since they possess inward velocity at horizon crossing. For a billion solar mass black hole with rs near 3 billion kilometers, the time extends to roughly 5,000 seconds or about 80 minutes. During this final interval, what does the observer experience? Tidal forces increase rapidly as radius decreases. The tidal acceleration proportional to mr3 grows without bound approaching the singularity. For stellar mass holes, lethal tidal forces appear quickly. For supermassive holes, the observer might survive conscious for tens of minutes inside the horizon, experiencing increasing stress before tidal forces become overwhelming. The observer continues seeing the external universe through light that fell in earlier. Photons from stars, galaxies, and other external sources fall through the horizon continuously. These photons can be detected by inside observers, carrying information about external events. However, the observer sees external events from progressively earlier times, never witnessing what happens after their own horizon crossing. Looking outward toward the direction of the horizon shows photons that crossed the horizon more recently than the observer. These appear blue-shifted to extreme energies due to the observer's motion through curved space-time. The compression of the external universe's light creates a brilliant ring of high-energy radiation that might prove dangerous or even fatal through radiation exposure. Can inside observers send signals to other inside observers? Yes, provided the geometric relationships allow causal contact. An observer falling slightly behind another observer in time can send light signals that catch up and are received, but an observer cannot send signals to observers who fell earlier because those observers lie in regions already causally disconnected. Their world lines have progressed to smaller radii, where light from later falling observers cannot reach. The singularity at r-equals 0 represents genuine space-time curvature becoming infinite, quite different from the coordinate singularity at the horizon. Here, general relativity breaks down. Tidal forces, space-time curvature components, and energy densities all diverge. The theory cannot predict what happens at the singularity itself, indicating that quantum gravity effects currently unknown must become important. Various scenarios for the singularity's nature have been proposed. The classical Schwarzschild solution predicts a point singularity at r-equals 0 where all infalling matter concentrates. However, this seems physically unrealistic. More likely, quantum effects prevent actual singularity formation, potentially creating exotic states of matter at Planck density approximately 10 to 96 kilograms per cubic meter, where spacetime's classical description fails. String theory, loop quantum gravity, and other quantum gravity approaches suggest that spacetime itself becomes discrete or fundamentally quantum mechanical at Planck scales near 1035 meters. These quantum effects might prevent infinite curvature, replacing the singularity with a quantum region where space and time lose classical meanings. The specifics remain speculative pending a complete theory of quantum gravity. The Cauchy horizon appearing in charged and rotating black hole solutions creates additional interior structure. Inside the inner Cauchy horizon of these solutions, the geometry becomes highly exotic, with closed time-like curves allowing time travel to the past. However, the Cauchy horizon appears unstable. Infinitesimal perturbations grow exponentially, likely creating singularities that prevent the exotic interior region from forming in realistic situations. The Penrose diagram, a conformal spacetime diagram compressing infinite regions to finite size while preserving causal structure, illustrates black hole geometry clearly. For Schwarzschild black holes, the diagram shows the external universe, the black hole interior, and the relationship between infalling and distant observers. The horizon appears as a 45-degree line, emphasizing its null character. The singularity appears as a space-like boundary at the top of the diagram. Inside, observers cannot escape, but can they communicate with other regions? The extended Schwarzschild solution includes a white hole region, the time reverse of the black hole, where matter can only exit, never enter. It also includes a second exterior region, another asymptotically flat universe. These additional regions probably don't exist in realistic black holes formed from collapsing matter. They represent mathematical artifacts of the eternal Schwarzschild solution. Realistic black holes form from stellar collapse or matter accretion. The spacetime geometry for these includes only the genuine exterior and interior regions, not the white hole or second exterior. Penrose diagrams for collapsing matter show how the horizon forms dynamically as matter contracts through the Schwarzschild radius, creating a causal boundary that grows to encompass the collapsed matter. Could an inside observer survive passage through a quantum-modified singularity to emerge elsewhere? Speculative scenarios suggest the singularity might act as a portal to another region of spacetime, possibly another universe or a distant region of our own universe. However, these remain purely conjectural. General relativity clearly predicts that classical singularities represent endpoints where world lines terminate and spacetime ceases to exist. The interior experiences time flowing toward the singularity in the sense that all time-like world lines end there. But this time refers to the radial coordinate, which becomes time-like, not the Schwarzschild coordinate t, which becomes space-like. The proper time measured along infalling world lines progresses normally, ticking away microseconds or hours depending on black hole mass until reaching the singularity. Information that crosses the horizon becomes inaccessible to external observers. Classical general relativity predicts that information about infalling matter's quantum state remains locked inside, disappearing when the singularity destroys it. If Hawking radiation carries no information about what fell in, information appears lost from the universe, violating quantum mechanics' unitarity requirement. Various resolutions to this information paradox have been proposed. Perhaps information encodes in subtle correlations in Hawking radiation. Perhaps the horizon develops microscopic structure that stores information. Perhaps information gets released when the black hole evaporates completely billions of years later. Perhaps black holes don't truly evaporate, but leave remnants containing the information. None of these solutions has achieved consensus acceptance. The firewall paradox adds additional complexity, questioning whether horizons remain smooth crossing surfaces as classical general relativity predicts. If information must emerge in Hawking radiation to preserve unitarity, quantum entanglement relationships might require destroying the smooth horizon, replacing it with a firewall of high-energy particles that incinerates in falling observers. This contradicts the equivalence principle's requirement that free-fall observers experience normal physics. Understanding black hole interiors pushes against the boundaries of current physics. Classical general relativity provides clear predictions: smooth horizon crossings, inevitable singularities, finite proper time from crossing to termination. But quantum effects, information preservation, and the ultimate fate of infalling matter remain open questions requiring physics beyond general relativity to answer definitively. The interior represents the ultimate unknown, a region where our physical theories face their limits and where empirical verification remains impossible since no information escapes to confirm or refute predictions. What happens inside can only be inferred from outside physics and from theoretical extrapolation of known laws into untested regimes. Coordinate systems and perspectives. Different coordinate systems describe the same curved spacetime geometry using different mathematical representations, analogous to how the same geographic location can be specified using latitude, longitude coordinates, Cartesian coordinates, or polar coordinates. Near black hole event horizons, coordinate choice becomes crucial because some coordinates become singular at the horizon while others remain well-behaved, affecting how clearly different physical phenomena appear in the mathematics. Schwarzschild coordinates using time coordinate t and radial coordinate r, along with angular coordinates th and f, provide the most intuitive description for distant observers at rest relative to the black hole. These coordinates naturally describe the static space-time far from the hole, where time translation and spherical rotation symmetries manifest clearly. The metric components in Schwarzschild coordinates show how space-time intervals relate to coordinate intervals. The Schwarzschild metric takes the form ds2 ors 1 rs r c2dt2 plus 1 rs r 1 dr2 plus r2 do2, where d1 represents the solid angle element and rs equals 2gm c2. This metric becomes singular at rhan rn, where the time coefficient vanishes and the radial coefficient diverges. These singularities are purely coordinate artifacts, not physical infinities, but they obscure what happens at the horizon from the Schwarzschild coordinate perspective. The coordinate singularity creates several problems. Radial light rays aimed outward at r's remain at constant radius, rather than escaping or falling inward, suggesting something special occurs there. The coordinate time required for infalling objects to reach Rs diverges, suggesting objects never actually cross. Observers attempting to remain stationary at Rs would require infinite acceleration, suggesting the horizon represents an infinitely strong barrier. All these suggestions mislead because they reflect coordinate pathology rather than physical reality. Alternative coordinate systems eliminating the coordinate singularity show that the horizon represents a smooth null surface that infalling observers cross without incident. The lesson emphasizes the importance of distinguishing coordinate-dependent mathematical features from coordinate-independent physical properties. Eddington-Finkelstein coordinates provide the first improvement. These combine the Schwarzschild time and radius into new coordinates that remain regular at the horizon. Ingoing Eddington-Finkelstein coordinates, useful for describing infalling observers, use time coordinate v equals t plus r, where r equals r plus rs, 10 rs. 1 charge represents the tortoise coordinate. This coordinate choice removes the singularity at the horizon for ingoing light rays and infalling particles. In ingoing Eddington-Finkelstein coordinates, the metric becomes ds2 wahagas 1 rsir c2 dv2 plus 2c dv dr plus r2 do2. Cross-term between dv and doctor eliminates the coordinate singularity at r's. Radial null geodesics for ingoing light follow dv dr 2 c1 rsr which remains finite at Rs infalling particle world lines, cross smoothly through R and Rs without coordinate singularities, outgoing Eddington-Finkelstein coordinates using retarded time, U, T, R, work better for describing outgoing light rays and the causal structure visible to distant observers. In these coordinates, outgoing radial null geodesics follow simple trajectories, while ingoing ones become more complex. The choice between ingoing and outgoing coordinates depends on which physical situation needs clearest description. Kruskal-Sekeres coordinates provide the maximally extended Schwarzschild solution, revealing the complete spacetime geometry, including regions inaccessible to any single observer. These coordinates, denoted U and V, or sometimes T and X, relate to Schwarzschild coordinates through expressions involving exponentials and hyperbolic functions. The resulting metric takes a simple conformally flat form, emphasizing the geometry's essential structure. In Kruskal-Sekeres coordinates, the metric becomes ds2, or t32g3m3 gr and exp r2gm dv2 du2 plus r2du2, where r is defined implicitly through u and v. The horizon appears as the lines u at 0 and v at 0, clearly showing its null character. The singularity at r pound 0 appears as the hyperbola uv partial 1 in the future of the black hole interior and uv partial 1 in the past of the white hole region. The Penrose diagram further compresses infinite spacetime regions to finite coordinate ranges while preserving causal relationships. Light rays always travel at 45-degree angles on Penrose diagrams regardless of spacetime curvature. This allows immediate visualization of causal structure, which events can influence which other events through time-like or null paths. For Schwarzschild black holes, the Penrose diagram shows 4 distinct regions, 2 exterior universes, 1 black hole interior, and 1 white hole interior. The 2 exterior regions connect through an Einstein-Rosen bridge, a wormhole that exists in the maximally extended solution but closes too quickly for traversal. Realistic black holes formed from stellar collapse include only 1 exterior and 1 interior, not the full extended solution. The white hole region, the time reverse where matter can only exit, never enter, doesn't appear in collapse scenarios. It represents a mathematical artifact of the eternal Schwarzschild solution. Choosing appropriate coordinates affects not just mathematical convenience, but conceptual clarity. Schwarzschild coordinates naturally describe distant observer perspectives where objects freeze at horizons and time dilation becomes infinite. Eddington-Finkelstein coordinates naturally describe infalling perspectives where crossing occurs smoothly in finite, proper time. Kruskal-Sekeres coordinates reveal global causal structure, showing how different regions relate. The lesson extends beyond black holes to general relativity's geometric philosophy. Spacetime exists as a geometric object, a 4-dimensional pseudo-Riemannian manifold with metric structure. Coordinates merely label points in this geometry, providing mathematical handles to calculate quantities, but not representing physical entities themselves. Physical predictions must be coordinate-independent, expressed through geometric objects like scalars, vectors, and tensors. Curvature scalars, quantities that remain unchanged under coordinate transformations, provide coordinate-independent measures of spacetime geometry. The Kretschmann scalar, formed from the Riemann curvature tensor, equals 48G2M2R6 for Schwarzschild geometry. This clearly diverges at r equals 0, confirming the physical singularity there, but remains finite at r pre-rs K.2GMC2, confirming that the horizon represents only a coordinate singularity. The proper time interval dt measured along time-like world lines, defined through dt2, Pais, dis2, c2, provides another coordinate-independent quantity. Calculating proper time between events along specific world lines gives the same result, regardless of coordinate system used for the calculation. The proper time for horizon crossing remains finite in all coordinate systems, even though coordinate time in Schwarzschild coordinates diverges. The distinction between coordinate and physical properties appears throughout general relativity. Coordinate velocities, like dr/dt, depend on coordinate choice and can exceed light speed or become ill-defined. Physical velocities measured locally by nearby observers always remain below light speed and have well-defined physical meaning. Coordinate singularities appear in poorly chosen coordinates but don't represent physical infinities. Physical singularities like r equals 0 appear in all coordinates and represent genuine breakdown of classical geometry. Understanding the horizon crossing. Paradox requires recognizing that time in the statement "crossing takes infinite time" refers to coordinate time in Schwarzschild coordinates specifically. Proper time along infalling world lines remains finite. Coordinate time in Eddington-Finkelstein coordinates also remains finite for crossing. Only Schwarzschild coordinate time diverges, reflecting that coordinate systems' singular behavior at the horizon. The apparent contradiction between finite and infinite crossing times resolves by recognizing that these refer to different time concepts in different reference frames described by different coordinates. There exists no absolute universal time against which all measurements must be compared. Time intervals depend on the specific spacetime path between events and on the coordinate system chosen to describe that path. The flexibility of coordinate choice, far from representing ambiguity or weakness in general relativity, demonstrates the theory's geometric nature. The same geometric structure admits multiple coordinate descriptions, each highlighting different aspects or adapting to different physical situations. Choosing coordinates wisely makes calculations simpler and physical interpretation clearer. For distant observers, Schwarzschild coordinates naturally describe their observations. For infalling observers, Eddington-Finkelstein coordinates better represent their experience. For understanding global causal structure, Kruskal-Sekeres coordinates or Penrose diagrams prove most illuminating. No single coordinate system handles all purposes optimally. Different questions require different mathematical tools. Practical implications. The extreme time dilation near event horizons creates practical consequences and thought experiment scenarios that illustrate relativity's predictions while raising questions about observation, causality, and the limits of physical law. Examining specific situations reveals how theoretical physics manifests in concrete examples, even if actual experiments remain technologically impossible. Consider a spacecraft orbiting close to a black hole event horizon at the photon sphere radius, 1.5 Schwarzschild radii, where the orbital velocity approaches light speed and time dilation becomes substantial. For a 10 solar mass black hole with Rs/Shi 30 kilometers, the photon sphere sits at R/Shi 45 kilometers. An astronaut orbiting there experiences gravitational time dilation factor 1 RSR/Shi 1, 2, 3, 0.577, meaning their clock runs at about 58% the rate of distant clocks. Additionally, orbital velocity at the photon sphere reaches approximately 0.866 times light speed, creating velocity-based time dilation factor 1 Chi3 Chi is 1 V2 C2 0.5. Combined, the total time dilation reaches approximately 0.577 x 5.29. The orbiting astronaut's clock runs at roughly 29% the rate of distant clocks. 1 hour for the astronaut corresponds to about 3.5 hours for distant observers. If the astronaut orbits for what feels like 1 day, approximately 3.4 days pass for distant observers. A 1-month mission subjectively becomes about 3.4 months externally. A 1-year mission becomes 3.4 years. The astronaut ages more slowly than people remaining far from the black hole, a dramatic manifestation of time dilation, though not infinite, as at the horizon itself. Could this enable time travel to the future? In a sense, yes. The astronaut orbits for 1 year subjective time, then returns to distant space where 3.4 years have elapsed. Friends and family have aged 3.4 years, while the astronaut aged only 1 year. The astronaut has traveled 2.4 years into the future, relative to people who remained far from the black hole. This represents time dilation, not time travel in the science fiction sense, but achieves similar effects. The interstellar film dramatized this concept with the planet orbiting close to the supermassive black hole Gargantua. The screenplay specified 7-fold time dilation. 1 hour on the planet equals 7 years distant. This requires orbit extraordinarily close to the horizon of an extremely rapidly rotating black hole, where frame dragging allows stable orbits closer than possible around non-rotating holes. The physics is correct in principle, though the specific numbers require very particular black hole parameters. Could civilizations use black holes as time machines to visit the distant future? Theoretically, yes. Practically, probably not. The engineering challenges of safely orbiting near event horizons, the intense tidal forces and radiation, and the impossibility of returning to earlier times limit practical applications. Time dilation enables one-way travel to the future, but not to the past. What about using gravitational time dilation for ultra-long-distance space travel? If astronauts could survive near black holes, they might experience brief, subjective time, while distant universe ages substantially, potentially allowing travel to epochs billions of years hence. However, tidal forces and radiation near stellar mass black holes prove lethal, and supermassive black holes producing survivable conditions at horizons lie only at galactic centers, difficult destinations for spacecraft. The information paradox creates practical questions about what happens to matter and information that cross horizons. According to classical general relativity, information falling into black holes remains trapped inside until destroyed at the singularity. Quantum mechanics demands information preservation. Unitarity requires that quantum states evolve reversibly without information loss. These requirements apparently conflict. If information disappears into black holes and Hawking radiation carries no information about what fell in, quantum mechanics' fundamental principles fail. Various resolutions have been proposed. Perhaps information does encode in Hawking radiation through subtle quantum correlations. Perhaps black holes leave information containing remnants after evaporation. Perhaps the horizon develops information storing structure. None has achieved consensus. The firewall paradox sharpens the conflict. Preserving information in Hawking radiation might require horizon structure that violates the equivalence principle's requirement of smooth crossing. If quantum entanglement relationships demand information release, the horizon might become a firewall of high-energy particles incinerating in falling observers. This contradicts general relativity's prediction of smooth crossings. Could we test these ideas observationally? Black holes exist throughout the universe, with supermassive examples at most galaxy centers and stellar mass examples scattered through galaxies. Observations of accretion, disk emission, gravitational wave signatures from mergers, and event horizon telescope images probe horizon structures. But quantum effects and information dynamics remain far below current observational capabilities. Falling into black holes provides no scientific value since information cannot return, but thought experiments reveal theoretical implications. If an astronaut carried a computer recording quantum states and fell in, does the information disappear? Can it be recovered from Hawking radiation? Does the firewall destroy the astronaut and computer before crossing? These questions probe the interface between general relativity and quantum mechanics. The ultimate fate of black holes through Hawking evaporation creates long-term practical implications. Stellar mass black holes evaporate over timescales exceeding 1067 years, far longer than stars will shine or galaxies maintain structure. But eventually, if the universe expands forever, cooling toward absolute zero, black holes will evaporate, leaving only radiation and possibly remnants. What happens to spacetime when black holes evaporate? Does the horizon shrink smoothly until the black hole disappears? Does it undergo phase transition to some exotic state? Does it explode when reaching Planck mass? General relativity cannot answer because quantum gravity becomes essential at these scales. Observing evaporation directly remains impossible given the timescales involved. Could advanced civilizations use black holes technologically? Energy extraction through the Penrose process with rotating black holes, using horizon areas for information storage, and gravitational time dilation for time shifting all appear theoretically possible. Whether practical engineering could implement such schemes remains unknown. Black holes provide extreme conditions potentially valuable for scientific experiments or applications requiring strong gravity. The possibility of extracting energy from black holes has been studied theoretically. Rotating black holes possess rotational energy that can be extracted through the Penrose process, where objects split in the ergosphere, with parts falling in, while others escape with more energy than initially possessed. This extracts black hole angular momentum, potentially providing immense power sources if engineering challenges could be overcome. Could naked singularities exist without event horizons? Cosmic censorship conjectures propose that singularities always hide behind horizons in physically realistic situations. If naked singularities could form from gravitational collapse, they would allow observation of regions where space-time curvature becomes infinite and general relativity breaks down. No observational evidence for naked singularities exists supporting cosmic censorship, though rigorous proofs remain incomplete. Wormholes, hypothetical space-time tunnels connecting distant regions, relate to black hole physics through Einstein-Rosen bridges appearing in extended Schwarzschild solutions. These wormholes close before anything can traverse them in classical general relativity. Exotic matter with negative energy density allowed by quantum field theory might stabilize traversable wormholes, but engineering such configurations remains pure speculation. Time machines using closed, time-like curves where paths through space-time loop to intersect their own past could theoretically exist in certain general relativity solutions, including rotating black holes' inner regions. However, these regions suffer instabilities and probably don't exist in realistic black holes. Whether time machines could exist under any physically realizable conditions remains an open theoretical question. The practical implications of horizon physics extend from fundamental questions about information and causality to speculative possibilities for future technology or distant cosmic futures. Near-term applications remain limited, but theoretical understanding reveals deep connections between gravity, quantum mechanics, and information that continue driving physics research toward unified theories of quantum gravity.